Alright, time for draftphysics.com, debatephysics.com also. But debate, it's rough to find any reasonable or fair or whatever debate, conversation, argument. People just won't do it. So anyway, one of the trolls, frankly, and that's all they are, has made a video, and it's just a really bad explanation of pulleys, and he's trying to imply that pulleys don't work, and he's using a mistake of mine, okay, and you know, doubling down on it, so to speak. It's fair game, but it's just stupid. So I'll just point out his video. He's just showing he's stupid by not just pointing out I was wrong to say it the way I said it, and to draw it the way I drew it. But pretend that somehow that is my argument, the wrong argument, when, yeah, I've drawn it 500 times the right way and I draw it once wrong way, and he uses that video. So I can't do much about that. So anyway, I don't know what video it is, but I guess I should find it and fix it, in the sense that point out how it's, not very useful because I described it absolutely backwards. I mean, I put the A where the B should have been. So if you look at the two diagrams displayed, yeah, I guess I can do that this way. I don't know. I guess I could use my pointer. But anyway, the top diagram, obviously, I have the little arrow where the big arrow is supposed to be, and the big arrow where the little arrow is supposed to be. So that's a big mistake. Obviously, the part that has two ropes on it is moving half the amount of distance in the same time as the one rope moves 2 units of distance. There's 2 velocity on one side, 1 velocity on the other side. And I put the weights exactly opposite. So that was my bad. But anyway, well, I'll just show you what he did on top of that. So just to point out how it's just a garbage video. None of his cronies pointed out how it's garbage and irrational and nonsensical, but whatever. I mean, the parallel to the mistake is this. Okay, I mean, to argue that there should be a balance and a lever when you put the 2 mass twice the distance and the 1 mass 1 unit of distance, obviously that's not going to balance. The light mass has to be where there's 2 units of distance, the heavy mass where there's 1. That's the balance. So yes, my bad. But like I said, his worse. So leave us continue.
Steve Mould's video was basically about. In the video, they basically argued and proved that pulleys work. They conserve momentum.
So that's the real point. So why didn't you just play the minute physics clip and explain how the minute physics clip that was in Steve Mould's video, how it proved 1.4? That you can't move that you can't move the 1 mass twice the velocity, that it'll only go 1.4 with the same force. So why don't you show where Steve Mould proved that, or minute physics proved that? Because they didn't. They didn't show in any way how pulleys don't perfectly conserve momentum and perfectly annihilate any notion of kinetic energy. The kinetic energy is not conserved. When you balance the pulleys, that is, you put a weight on one side that balances the weight on the other, so it would be a 2-to-1 relationship. So the 2 mass would be here, the 1 mass here, and they'll balance perfectly. Essentially, you have a counterweight, and the half mass technically weighs the same as the double mass, and you could just, the only force you have to overcome is the resistance in the pulleys, the friction. So you can lift 100 pounds without doing any work, as long as you have the 50 pounds already lifted. So that's the trick of it. The 50 pounds will move with 2 velocity. The 100 pounds will move in the opposite direction with 1 velocity. Very nice gimmick, trick, and that's all. There's no free energy involved. But by their theory, you're applying twice the energy on one side that you're applying on the other side. So there is no balance. by kinetic energy's notion of reality. Alright. Somehow there's twice as much energy in this object going this way and half the energy in the other object going the opposite direction. And that obviously isn't true. Alright, continuing.
And they violate kinetic energy. So the simple truth is you can put a force here in this direction and you'll get twice the energy, okay, in the sense of you can have the lighter object. So I can make this a 10 and this a 5.
So, my mistake. It's obviously should have been exactly the opposite.
Alright. And the 5 mass will move. For any movement in the 10 mass, I'll get twice the motion in the 5 mass.
So obviously I'd only get half the motion in the 5 mass. So, again, my mistake.
Mass. And vice versa. So I can move the 5 mass up and down. And I can make the 10 mass move 1/2 the velocity up and down. Or vice versa. Indicating it's completely momentum driven.
I don't need to put weights, per se. I can just use a force meter and I'll detect exactly that it's an equality. I can't fix the fact that it's going to end up being equal.
There's no evidence that kinetic energy can be reasonably applied because
it's a lever. It's just another form of leverage. So the only thing you're doing is just converting a big M and a small v on this side into a small mass, small m, and a big V on the other side. And that's all levers and pulleys do, is convert one form of mv into another form of mv that has exactly the same total. So you can never change how much force there is. You can only change how it's applied, in what unit of time.
Frankly, I put a
Or at what velocity.
force in this way and I get twice the energy out this way, or I put a force in over here and I get half the kinetic energy out on the other side.
Now that remains true, so that they didn't fix. They can't change that truth, that kinetic energy fails to create a rational balance. By their theory, a half mass out here will compensate a 2 mass here. So a 2 mass going 1v will be the same as a half mass going 2v by kinetic energy. And you know that won't work. It plainly won't work. Won't balance.
It makes no sense. So somebody draw me an example of pulleys not conserving momentum. Completely, reliably, dependably, and always. Show me where kinetic energy works in here somewhere, because it doesn't.
Here's the weighing of the masses.
Alright, so we'll skip this because that's just plain boring. So he has the 2 mass in the wrong relationship as stated. So he's got the 2 mass on the wrong side and the 1 mass on the half the velocity side.
Show the point.
And they're not pulleys, so he's just got ropes over pieces of steel, so it doesn't work. So there's no actual gravity experiment here or anything. It doesn't work. The balance doesn't balance. So in other cases they use big giant weights for little tiny experiments, and in this experiment where he could use a big giant weight, he's using little weights. So explain that one to me, please.
So on this rod, the entire length of the rod is 54 centimeters. There's a marking there at 27, which is half of the rod, and the 2 mass should be dropping, but I'm going to have to pull it down.
So by this experiment, it has 4 times the energy, frankly. It should really easily pull the other thing up because you have the heavy mass on the mechanical advantage side. So it's you should have a real disproportion. You have 4 times the weight essentially on one side that you have on the other side. And even with that huge differential, it still won't move on its own. He has to move it. So the friction is so bad. I mean, it's string just going over pieces of metal. So yes, it's just not going to work. There's no real pulley anywhere.
So that will be going half the distance of the rod. Now on the other side, it would have to reach the top.
So you can see the rope is just looped over a piece of steel, so it's really a lot of friction. Huge, gigantic, monstrous.
Of the rod in the same amount of time, because obviously as this move in the same amount of time.
So he's going to draw it the opposite way later, and that's the real ironic part. So he's going to switch it when he does the drawing to the right way, having the heavy mass on the 1V side and the light mass on the 2V side.
Move a distance. If it moved to the top of the rod, it'd move twice the distance.
I think when he introduced this, he said this is a 2-to-1 pulley. So even conceding the 2-to-1 pulley, calling it a 2-to-1 pulley, it's just you already gave away the right answer. It's not a 1.4-to-1 pulley.
In the same amount of time, therefore it began twice the velocity. I've got to employ the use of the head cam for this one because I need both hands. So it's really difficult through the camera. So
this is less than a drawing, I would say, right? Because the whole thing doesn't work at all, and so it illustrates just about nothing.
So like I say, we'll have to imagine that these would drop.
I mean, just we already know that this side's going to move twice the distance that the other side moves in the same time. So he's just showing that how levers work, that the end moves twice as much as the part here. So yeah, that wasn't in dispute, I don't think, by anybody.
So that's roughly at half the distance of the rod. And if it was to fall,
yeah, let's all pretend.
The other side goes up. And eventually.
So again, this is 1/4 of the work to lift this 1 unit of distance. Is 1/4 of the work that the other side would be doing, frankly, if it was falling in gravity. So it's going to fall quite rapidly because this is so easy for it to move. It's the 2 mass out on the lever. The 2 mass further out can move the 1 mass inside really easily. Won't be any work at all.
We see that it's around about half.
But even with his configuration being completely backwards and being a huge disproportion 4-to-1, it still didn't work. I mean, he still couldn't get it to move on its own, which is so ironic.
The distance. So that fell twice the distance of this one went up. So
nothing fell, and the whole thing is just bullshit.
We were to consider momentum, obviously, if this was to fall, boom, and this one goes up, this went twice the distance, and it's a 2 mass. This went half the distance, and it's a 1 mass.
Right, so you didn't show anything. Yes, 4 times the weight will move 1 unit of weight really easily, except in your experiment.
So momentum is not conserved in pulley systems.
So of course it would be if you just switch the weights. Then you would have just illustrated it perfectly.
Like I say, ideally, if it hadn't got so much friction, I could just drop it and boom. But as you can see, it only reaches half the distance, not twice.
We know that already, so that's exactly how it's supposed to work, yes. One side is 1 unit of distance, the other side is 2 units of distance, and if it was a 3-to-1 pulley, then it would be 3 units. And,
the distance, half the distance, twice the distance would be to the top there, because it's falling from half the distance of the rod here, so twice the distance would be the top. And obviously inversely, if it's to pull this down, the 13.5 centimeters.
So it's a lot more work, is what he should be saying. Well, this side's a lot harder to pull. That he should be pointing that out, because he's lifting a very heavy weight. Okay, and he's lifting it more velocity. So one side was 4 times more work to move than the other side. I mean, they're, you know, inverted.
This one goes up to a distance of half the rod again, so what was it, 13.
So he called it, like I said, he started the video by calling it a 2-to-1. So we already know it's 2-to-1. So this is not a surprise.
527. So it's a complete inverse of what you're claiming.
So what I'm claiming is that the Minute Physics video didn't show any evidence that levers don't conserve momentum, and instead basically mathematically prove they do. And so that's the substance of the argument. But obviously I made a mistake in drawing it backwards.
So momentum is not conserved in pulley systems.
So that's his conclusion. So because I drew it backwards, he did it backwards. He didn't really do the experiment, and he certainly didn't demonstrate anything qualitatively. And yet he's making the declaration that somehow he demonstrated that levers don't conserve momentum, when yes they do. Perfectly.
Which is quite clear.
Very well.
But energy is. From the depth.
So energy wasn't. He didn't show us anything indicating that the kinetic energy is in any way conserved. So that wasn't in there anywhere. So here's his drawing.
Well, we can see we had the two mass moving, just call that one distance in.
So he's saying it exactly backwards. He had the 2 mass doing 2 distances and the 1 mass doing 2.
One unit of time, and the 1 mass moved.
Okay, he said half. All right, so that is what he did. So it's, yes, this isn't how you use levers traditionally. Okay, you're talking about trying to create a balance, not trying to create a 4-to-1 imbalance.
Half that distance in 1 unit of time, so the 1
And I certainly didn't claim those things would be equal. So
mass is going half the velocity. So if we look at that in terms of momentum, we've got, just say, 2 mass going 2 velocity and 1 mass going 1 velocity. So we'd have...
it'd be even worse with kinetic energy. So kinetic energy ain't going to make that any worse. It's just going to make it 8-to-1.
A momentum of 4.
So do you think you showed 8-to-1? No, you didn't. So fail.
Or and a momentum of 1. So clearly momentum in pulley systems is not conserved. If we just take a look at this in terms of energy.
So now he's got it right. He's got the 50 Newton, the small weight on the outside, and the heavy weight on the 2 rope inside. And so now he's really in trouble, because this is impossible to say it doesn't conserve momentum perfectly, because it perfectly conserves momentum. The heavy mass, the 2 mass, will move 1 velocity, and the 1 mass will move 2 velocity. So he's just proving exactly what I said. So now this drawing matches this drawing. The 2 match now.
That's the pulley system. So we've got a mechanical advantage of 2. Just say the weight here was 100.
So he's conceding it's a mechanical advantage of 2. The only way kinetic energy could balance is I'd have to put a 25 mass, not a 50. So he's got a 50 Newton mass. To balance kinetic energy, I'd have to have a 25 Newton mass on this side. You know, because of the squared velocity. The 2 velocity is going to be squared to 4. And the only way I can, balance that is you have to reduce the mass. So a half mass, a quarter mass will balance using kinetic energy. Now we know it won't, so we know kinetic energy isn't true because it won't balance with kinetic energies being balanced. If I balance the kinetic energies on both sides, it won't balance. The 2 won't be the same. I won't be able to move the weight anywhere and have it stay balanced. I mean, that's the great thing. But this is, like I said, a counterweight system. So you're not actually supporting the weight because you have created a counterweight. So essentially, the only thing you could add any force, and the force you're applying is just going to be against the friction that's in the system, because the system itself is in perfect balance.
100 newtons. Obviously, we've got two ropes pulling it up, so we've got 50 newtons here and 50 newtons here, which would equal the 100. But we've got a weight of 100 newtons.
Right, so that weight's going to move 1/2 the distance. The 50 Newton weight's going to move 2 units of distance, perfectly conserving the momentum.
So the whole point of this system is to make it easier, because we've got 100 newtons of force, but when you pull on the rope, you only have to pull with a force of 50 newtons.
So you don't have to pull with 50 newtons if you have 50 newtons on the string already. So that's the great thing about it. Like I said, it's a counterweight. And so now you can lift 100 pounds without doing hardly any work at all. But of course you have to lift the 50 newtons back up again. All right, so I mean you have to prime your system, so it's not for free. But the mechanical advantage is essentially for free, in the sense that your inability to, it's like throwing something faster, right? If I have a ball on a stick, I can throw the ball twice as fast or 3 times as fast as I could throw it.
Makes lifting something that's heavy, you apply less force, but obviously you've got to do it over twice the distance, because obviously when you pull this rope's moving up and this rope's moving up, so twice the distance on the pulley here. When you pull it down, will only go up 1 unit of distance here.
Right, and so the distance is velocity, and it just makes more sense to quit talking about the distance and just talk about the velocity. So the velocities are exactly 2 to 1.
So the force would be 50 newtons over twice the distance to lift.
So if he did this, he'd end up with the 50 newtons over here going 2 units of velocity, which means that gets squared. So the kinetic energy is twice the kinetic energy. It will somehow be on this side. And when this is moving up, it will only have 1 unit of kinetic energy.
This 100 newton weight force up 1 distance or 1 displacement. Obviously work is force times distance.
Yeah, well that's just nonsense, but whatever. There's no distance involved in zillions of experiments. A gun, for example, you don't measure, there's no distances to measure. The velocities are obtained almost instantaneously. There's no over any distance, there's no rate of acceleration, none of that crap is real. It doesn't have anything to do with anything.
So the weight itself that's being lifted is a weight force of 100 newtons, and it would displace 1 distance.
1 velocity. Yeah. So it's going to be a weight, a mass moving a velocity, and it's going to be a momentum. So he's basically just proving conservation of the momentum here by just clearly pointing out it's a what you could say a 2 mass going 1v and a 1 mass going 2v equals the same amount of momentum.
So energy wise that would be 100 on the...
So he's proving the conservation of momentum. Just clearly right there proven. And then he's saying he's proving it isn't conserved. So you get the I mean, it just doesn't get much worse than this.
Where you're pulling it, obviously you've got the reduced force, but you're pulling it for twice the distance. So
yeah, so I'm just saying, so one of the commenters did point out, well, you did prove conservation of momentum in the end of the video. Yes, and it's right there. And he says, well, I'm confused. What do you mean? Well, it's right there. Your numbers. You got a two mass going one velocity, and you have a one mass going two velocity. There, you're done.
Got 50 newtons of force over twice the distance, and that equals 100. So the energy is conserved.
So kinetic energy is not conserved. Those numbers, okay, because of that two distance, that two velocity, that means it's four velocity, all right? And so it's going to end up being, the kinetic energy number would be 200. So if the kinetic energy for the heavy object was 100, the kinetic energy for the light object is going to be 200. So he's just lying to say the kinetic energy is conserved. It's not conserved. The two sides of this balance, it's actually balanced, and they're basically arguing that one side of the balance has twice the kinetic energy that the other side has. Any movement in the balance, any change or alteration of the balance, you will have twice as much kinetic energy on one side as you have on the other. So, pile of crap. Alright. So anyway, that was bizarre is what it was. To see what other videos he has. But they're just so bad. They were talking about the lever launcher in the comments, and Despar mentioned he did two versions of it, and they were the crappiest, like popsicle stick crappy versions, and he was shooting things off a cliff, which is the good idea. Remember the Gosling video where he said, twice the velocity goes four times the distance, and he left that video up. Anyway, but he was doing these nuts and bolts things taped together, and it was so obvious that this little stick he was hitting them wasn't hitting in the center of mass, and the surfaces are sloped, and so you could just imagine they were flying up in the air. So obviously, if you shoot something in the air, it'll go further than the two velocity. I mean, you're not going to get a good reading of its actual velocity because you're going to change how far it'll go based on the launching direction. You'll give it more time to fall in gravity, essentially. More time to go that way. But anyway, so those are terrible videos. So no one's redone. Look, Brozo went to the trouble, right? I mean, he sawed off the two sides of a billiard ball. Did it. An experiment that could have been quite credible, and too bad he couldn't film it reasonably. But anyway, and of course the results were so close. 19 and 11, pretty close to 20 and 10, pretty close to 2 to 1. So anyway, but yes, please, somebody do more lever experiments and pulley experiments, because frankly, they are rock solid in terms of demonstrating conservation of momentum and demonstrating there's no such thing as kinetic energy. Alright, so till the next time, I guess that's enough. So, yeah, that's that's enough. Till the next time and such.